Okay, we're at section 31.4, mutual inductance, and let's share the PowerPoint. Okay, we have a configuration here similar to what you did your experiment. You have a current in coil 1, sets up a magnetic field, and uh, some of the magnetic field lines pass through coil 2. Now we know that if it's a steady state, that um, you won't get an induced current. You won't get an I2 in coil 2. But if it is a changing magnetic field, you'll get what is called mutual inductance, and the mutual inductance of coil 1 to 2, M12, is equal to the number of turns in 2 times the magnetic flux, phi12, times the current, divided by the current, I1. Now, E2 is equal to minus N2, Faraday's law. E2 is equal to minus N2 d phi dt, the change in magnetic flux, minus in phi. You can see from the blue rectangle above, phi12 is equal to M12 times I1 divided by N2. And you can see that the N2s cancel. And so you're left with E2 is equal to minus M12 di dt. You can also, we can reverse the process, and we'll see that E1 is equal to minus M21 di2 dt. And really they're the same. So really it's just an M. So E2 is equal to minus M di dt, di1 dt, and E1 is equal to minus M di2 dt. And this is very similar to the self-inductance that we saw, where E is equal to minus L di dt. And so M is mutual inductance, and it is expressed in henries. So in the figure, coil 1 is moved closer to coil 2, with the orientation of both coils remaining fixed. Because of this movement, the mutual induction of the two coils, does it increase, decrease, or is unaffected? Well, you can see that as it moves closer, more magnetic field lines are going to go through coil 2, so the mutual inductance increases. And that is the case. Okay, now we're going to stop here and go on to LC circuits.